Apache Spark is a distributed data processing framework designed for speed, scalability, and flexibility. It processes massive data sets quickly by leveraging in memory computations, fault tolerance, and easy to use APIs. For more tech interview materials, please visit our website, baozi8.com. Core components include 1. Spark Core, responsible for basic task scheduling, memory management, and distributed processing. It operates around RDDs, resilient distributed datasets, which are immutable collections of objects spread across a cluster. Enables fault tolerance through lineage, allowing RDDs to recompute lost partitions. 2. Libraries built on Spark Core. Spark SQL, used for processing structured data with SQL queries or through the data frame and dataset APIs. Spark Streaming processes real-time data streams from sources like Kafka or socket connections. MLlib Spark's machine learning library, offering tools for classification, regression, and clustering. GraphX supports graph processing and computation, useful for social network analysis. 3. Cluster managers. Spark integrates with Yarn, Mesos, or its standalone cluster manager to allocate resources and manage workloads. 4. Execution Environment Driver Program, the central orchestrator for jobs maintaining the application state. Executors, worker nodes that run tasks and hold in-memory data. Communication happens between the driver and executors. How Apache Spark works under the hood. 1. Data partitioning. Input datasets are divided into partitions and distributed across nodes in the cluster. 2. RDD transformations and actions. Transformations, e.g. map filter, are lazy, creating a logical DAG, directed acyclic graph of operations. Actions, e.g. collect, reduce, trigger execution, at which point the DAG is broken into stages and sent to executors. 3. Execution flow. Spark converts the DAG into tasks, optimizes them, and schedules their execution. Tasks process partitions in parallel across worker nodes. 4. In-memory processing. Unlike Hadoop's disk-heavy MapReduce, Spark loads and processes data in memory, achieving significant speed-ups. Example use cases are ETL pipelines, extracting data from databases, transforming it with Spark SQL, and loading it into data warehouses. Real-time analytics, processing IoT data streams using Spark Streaming for real-time anomaly detection. Machine learning, training models on massive data sets using MLlib. For example, building recommendation systems for e-commerce. Graph processing, social network analysis, or modeling delivery routes using GraphX. Pros include 1. Performance. In-memory processing drastically reduces latency. 2. Rich libraries. Built-in support for SQL, machine learning, and graph computations. 3. Fault tolerance. RDD lineage ensures data recovery after node failures. 4. Multi-environment support. Works on premises and on cloud platforms. Cons include 1. Memory intensive. High memory requirements may lead to resource contention. 2. Steep learning curve. Advanced APIs can be challenging for newcomers. 3. Cost. Memory and computational resources increase operational expenses. Thanks for watching. For more tech interview materials, please visit baozi8.com. Apache Kafka is a highly popular distributed event streaming platform designed to handle real-time data feeds. It is widely used for building robust data pipelines, streaming applications, and messaging systems. Kafka excels at high throughput and fault-tolerant data streaming. For more tech interview materials, please visit our website, baozi8.com. Core components include 1. Topics. Kafka organizes messages into topics, which are the primary unit for categorizing and managing data streams. For example, a topic named user activity might store all user interactions on a website. 2. Partitions. Topics are divided into partitions for scalability. Each partition is an append-only log where messages are stored in order. Partitioning allows Kafka to distribute data across brokers, enabling horizontal scaling. 3. Brokers. Kafka brokers are the servers that store data and manage message delivery. A Kafka cluster typically consists of multiple brokers. 4. Producers. Producers are clients that publish data to Kafka topics. They decide which topic and partition to write data to, often using a partitioning key to ensure related messages go to the same partition. 5. Consumers. Consumers subscribe to topics and process messages. Kafka's consumer groups allow multiple consumers to share the workload by consuming from different partitions. 6. Zookeeper or K-Raft. Zookeeper was traditionally used for managing metadata and coordination tasks like partition leader election. Kafka is transitioning to KRaft, a built-in mechanism for metadata management. 7. Replication. Each partition has a leader and replicas for fault tolerance. If a leader fails, a replica takes over, ensuring no data loss. How Kafka works under the hood. 1. Message ingestion. Producers send records messages to Kafka. Each record contains a key, value, and metadata. Kafka appends these records to the appropriate partition of a topic. 2. Partition leadership. A leader partition on a broker handles all read-write requests, while replicas act as backups. 3. Data storage. Kafka stores messages persistently on disk and retains them for a configurable retention period. This durability allows consumers to process messages even if they are delayed. 4. Message consumption. Consumers fetch messages from Kafka by polling. Each consumer tracks its own offset, the position in the log from which it reads. 5. Replication and fault tolerance. Data is replicated across brokers, ensuring availability during failures. Kafka ensures consistency by electing a leader for each partition and syncing replicas. 6. Scalability. Kafka partitions enable parallelism by allowing multiple producers and consumers to operate simultaneously. Adding more brokers improves throughput. Example use cases are event logging and analytics. Companies use Kafka to capture website clickstreams for real-time analytics. Microservices communication. Kafka acts as a message broker, enabling asynchronous communication between microservices. ETL pipelines. Kafka is commonly used to extract, transform, and load large datasets across systems. IoT data streaming. Kafka ingests sensor data from IoT devices for monitoring and processing. Database change capture, CDC. Kafka captures changes in databases and propagates them to other systems for synchronization. Advantages include 1. High throughput. Kafka can handle millions of messages per second with low latency. 2. Durability. Data is stored on disk and replicated across brokers for reliability. 3. Scalability. Kafka can scale horizontally by adding brokers and partitions. 4. Versatility. It supports both real-time streaming and batch processing. 5. Fault tolerance. Partition replication ensures data availability during failures. Disadvantages include 1. Operational complexity requires expertise to configure and monitor at scale. 2. Ordering guarantees. Kafka guarantees order only within individual partitions, not across them. 3. High resource usage. Brokers and Zookeeper require significant computational and storage resources. Thanks for watching. For more tech interview materials, please visit bowsy8.com. Apache Druid is a high-performance distributed database designed for real-time analytics and querying massive datasets. For more tech interview materials, please visit our website, bowsy8.com. Core components include 1. Data ingestion. Batch ingestion integrates with Apache Hadoop or file systems like S3 for loading historical data. Real-time ingestion uses Kafka or other streams to continuously process data into segments. Roll-up. Data aggregation reduces storage needs by combining similar rows based on a time granularity and dimensions. 2. Storage, deep storage. Reliable storage, e.g. S3, HDFS, where Druid keeps the immutable segment files. Historical nodes. Load and cache segments for query processing, improving access speeds. 3. Query layer. Broker nodes. Act as intermediaries for queries, routing requests to the right nodes. Query execution. Queries use columnar storage for faster aggregations with optimizations for scans, filter, and time series analysis. 4. Cluster management. Coordinator node oversees data placement, balancing segment loads, and ensuring retention rules are followed. Middle managers handle real-time ingestion and indexing tasks. What happens under the hood? 1. Data ingestion. Real-time streams or batch files are parsed and converted into column-oriented segments. Roll-ups aggregate data to predefined granularity for better query performance. Segments are replicated for fault tolerance and distributed across historical nodes. 2. Query execution. SQL-like queries are submitted to broker nodes, which decompose the query and distribute it across historical and real-time nodes. Results are merged at the broker and returned to the user, ensuring low-latency responses. 3. Scalability and fault tolerance. Druid supports horizontal scaling by adding more nodes to handle ingestion or query workloads. Segment replication ensures resilience to node failures. Example use cases are Ad tech analyze billions of ad impressions in real time to optimize campaigns and bidding strategies. Monitoring systems build dashboards for metrics and logs, offering interactive analytics for operational insights. IoT process sensor streams to deliver time series trends for predictive maintenance. Advantages include 1. Real time analytics handles high speed ingestion and low latency queries effectively. 2. Optimized for aggregations, excellent for time series, filtering, and group by queries. 3. Scalable and fault tolerant, designed for petabyte scale analytics with robust failover mechanisms. Limitations include 1. Operational complexity requires expertise to configure and tune ingestion and query pipelines. 2. Not fully OLTP compatible, primarily focuses on analytical workloads, not transactional operations. 3. Storage overhead. Rollups can result in reduced granularity if not carefully planned. Thanks for watching! For more tech interview materials, please visit bowsy8.com. Apache Airflow is a robust open source tool for orchestrating complex workflows through directed acyclic graphs, DAX. For more tech interview materials, please visit our website, bowsy8.com. Core components include 1. Directed acyclic graphs, DAGs, define workflows where tasks execute in a specific order. Dependencies are explicitly outlined, ensuring no cycles, feedback loops. Written in Python, offering flexibility and integration with various libraries. 2. Scheduler orchestrates task execution by determining the right time to run each task based on dependencies and schedules, continuously monitors the state of tasks to ensure smooth execution. 3. Executors execute tasks. Options include sequential executor, single-threaded, useful for testing. Local executor runs tasks in parallel on a local machine. Celery executor distributes tasks across multiple worker nodes for scalability. Kubernetes executor runs tasks in isolated Kubernetes pods. 4. Workers responsible for executing the actual tasks. Workers pull the task queue for jobs. 5. Metadata database stores the state and metadata of workflows, e.g., DAG definitions, task logs, execution results. Common databases include PostgreSQL or MySQL. 6. Web UI, a user-friendly interface to monitor DAGs, inspect logs, and manage workflows interactively. What happens under the hood? 1. DAG creation. Developers define workflows as Python scripts. Each task within a DAG is represented as an operator, e.g., bash operator, Python operator. 2. Task scheduling. Based on the defined schedule, e.g., daily, hourly, the scheduler queues tasks for execution. 3. Task execution. Tasks are dispatched to workers through the executor. Logs and states are updated in the metadata database. 4. Monitoring. Users can track task progress, check for errors, and rerun failed tasks via the web UI or CLI. Example use cases are data engineering, automate ETL, extract, transform, load pipelines for data processing. Machine learning, schedule model training, testing, and deployment workflows. Data quality, run regular validations on datasets. DevOps, manage infrastructure or CI/CD pipelines. Advantages include 1. Highly customizable, fully programmable in Python, allowing dynamic and complex workflows. 2. Extensible, supports plugins and integrations with third-party systems. 3. Scalable, handles workflows from small to enterprise scale using distributed executors. 4. Visual interface, offers easy-to-use monitoring tools via its web UI. Limitations include 1. Setup complexity, requires configuring multiple components, scheduler, workers, database. 2. Resource intensive, running workflows at scale can be hardware demanding. 3. Dependency management. Task interdependencies need careful planning to avoid bottlenecks. 4. Debugging overhead. Troubleshooting failures in complex workflows can be challenging. Thanks for watching! For more tech interview materials, please visit bowsy8.com. Apache Arrow is an open source data framework designed for fast, efficient, and cross-language data processing. It provides a columnar memory format and tools that help modern big data systems to process data at scale without incurring serialization, deserialization overhead. Its ecosystem supports various programming languages like Python, Java, C++, Go, and R, making it a highly interoperable tool in analytics and machine learning workflows. For more tech interview materials, please visit our website, bowsy8.com. Core components include 1. Columnar memory format. Arrow stores data in a columnar format, enabling efficient CPU cache usage for analytics and minimizing read time for columnar operations like filtering and aggregations. 2. Zero copy interprocess communication. Using a shared memory model, Arrow eliminates the need for copying or serializing data, enabling zero copy reads and writes across multiple processes or systems. 3. Language bindings. Arrow offers libraries for Python, PyArrow, Java, C++, and more, allowing seamless integration into diverse applications. 4. Plasma Object Store, an in-memory object store built into Arrow that supports large-scale distributed object storage with zero copy sharing. 5. Arrow Flight, a protocol for fast, lightweight data transport between systems, especially useful in analytics pipelines. What happens under the hood? 1. Data storage. Arrow stores datasets in contiguous blocks of memory in a columnar layout. Each column can be independently processed, which is optimal for workloads requiring operations on a subset of columns. 2. Schema management. Arrow ensures a consistent schema across systems, enabling compatibility without needing schema transformations. 3. Data sharing. Arrow uses memory mapped files to share data between processes without copying, reducing latency and improving throughput. Above 4, integration with ecosystems. It integrates with big data tools like Pandas, Spark, Dask, and Parquet. This allows seamless transitions between in-memory and on-disk storage formats. Example use cases are big data analytics, facilitates efficient data transfer and computation in frameworks like Spark and Pandas. Machine learning pipelines speeds up the pre-processing and transfer of massive data sets. Data serialization, used to serialize datasets for cloud storage or distributed processing. Real-time analytics, powers in-memory analytics for real-time data processing. Advantages include 1. Performance. Columnar storage enables faster queries and in-memory computations. 2. Interoperability. Works seamlessly across multiple programming languages and data platforms. 3. Efficiency. Reduces memory footprint and serialization-deserialization overhead. 4. Ecosystem support, integrated with numerous big data tools and databases. Limitations include 1. Learning curve, advanced understanding required to fully utilize its features. 2. Resource intensive, large memory consumption can be a challenge for constrained systems. 3. Specialized usage, best suited for analytical workloads, not ideal for transactional processing. Thanks for watching! For more tech interview materials, please visit bowsy8.com.